We've eagerly anticipated this as physicists for more than a century. Since 1916, this event marks a groundbreaking accomplishment, providing a glimpse into one of the universe's most mysterious and fascinating phenomena: black holes. These cosmic giants, known for their immense power, continue to be extremely elusive. While they are colossal in terms of gravitational pull, they are almost unnoticeable to us, which makes them even more enigmatic. A similar black hole, possibly weighing between 2 and 4 million times the mass of our Sun, might be the focus of this investigation. Over the past few decades, research on black holes has changed our understanding, taking us from a position of absolute ignorance to one where we are beginning to become more intimate with these objects. Take a look at them, and things have changed. An even more thrilling turn came when physicist Michio Kaku revealed that we have finally managed to peer inside a black hole. This revelation opens up a wealth of new information that may provide insight into aspects of science that previously might have been overlooked. Let us take a deep plunge into the depths of the black hole and discover what they contain. While space is boundless and vast, the concept of black holes generates numerous questions. Before we dive into the specifics of Kaku's remarkable findings, understanding the fundamental nature of black holes is essential. Most people have at least a basic comprehension of black holes, but significant gaps in our knowledge still remain. The theory of black holes dates back to 1916, when Albert Einstein published his general theory of relativity. This theory predicted the existence of black holes. Despite this prediction, the idea was purely theoretical. It wasn't until about 50 years later, during the 1960s, that concrete evidence for their existence first became apparent. Researchers, while observing the constellation known as Cygnus, detected an anomalously bright blue star emitting X-rays. They discovered that the star was not stationary, but was instead orbiting a huge black object. Upon further analysis, it became clear that these X-rays were being drawn into this object, leading to the coining of the term black hole. This discovery was a monumental turning point because it confirmed that black holes were not just a product of Einstein's imagination. They were real, physical entities that existed in space, and it became evident that we needed to learn more about them thoroughly. Researchers from all over the world began to focus their efforts on a particular black hole in the Cygnus constellation, designated Cygnus X-1, which lies approximately 6,000 light-years away from Earth. This black hole was approximately 14 times as massive as the Sun and exhibited a high density and gravitational pull so intense that not even light could escape it. This was the defining characteristic of a black hole: the capacity to ensnare light within its gravitational grasp. The concept of a black hole is simultaneously fascinating and terrifying. It is a region in space where gravity is so powerful that not even light can avoid it. Any object that ventures too close to a black hole is sucked in. Once it crosses a critical threshold, it is lost forever, never to be seen again. Because of the inherent danger, it's critical to expand our understanding of black holes. After the discovery of Cygnus X-1, researchers began a thorough search for additional black holes. Estimates now suggest that there may be over 100 million black holes scattered throughout the Milky Way galaxy. But because of their nature, these cosmic giants are exceedingly difficult to detect, meaning that we don't have a precise count. What is clear, though, is that millions of black holes could be lurking within our galaxy, underscoring their importance in cosmic research. The principal concern regarding black holes revolves around their gravity. The force of gravity is so great that anything that gets too close is gradually compressed to an extreme degree until it becomes a singularity. To put it simply, black holes function as cosmic vacuum cleaners, pulling in everything with a force that can't be stopped. One of the most alarming aspects of black hole theory is what would happen if someone were to fall into one. They would be stretched out into an elongated form due to the tidal forces acting on them. This process of stretching would be gradual, and the individual would die before reaching the process's final stage. So let's be clear, it's best to avoid falling into one at all costs. Despite the fact that the closest known black hole is 500 light-years away, this still raises questions concerning the potential threats they pose to us. In 2021, a remarkable milestone was achieved by scientists when they successfully captured the first clear image of a black hole. This particular black hole was located in the galaxy M87. The research team took multiple images over several nights, stitching them together into a comprehensive photograph that revealed shocking information. It revealed that a black hole is not simply one giant void of nothingness, as many people might think. In fact, a black hole consists of three distinct layers. The first layer is known as the event horizon. Once crossed, there is no way to return. Anything that passes it is inevitably drawn into the black hole. The second layer is referred to as the photon sphere, a region in which light itself can be trapped in orbit. Any light entering the black hole must go around it. This area becomes ensnared by the black hole's gravitational force, unable to escape. The final layer is the singularity, where everything that falls into the black hole is crushed down to a point of infinitesimally small size. Here, the established physical laws break down entirely, and it's impossible to predict what might occur. What is even more intriguing and troubling is that no two black holes are exactly the same. While they all adhere to this three-layer structure, the way they operate can differ dramatically from one to another. Normally, scientists observe objects in the sky through telescopes. But when it comes to black holes, this method is not practical because black holes are invisible. They can only be studied indirectly by observing the radiation and the surrounding gas and dust they interact with. Sending Voyager-class probes to explore a black hole is out of the question, as anything that crosses the event horizon would be drawn into the singularity and obliterated. Therefore, scientists must study these extraordinary objects through a two-dimensional lens, despite their inherently three-dimensional nature. One theory regarding the formation of black holes is that they are the result of collapsing stars. When a star burns through all of its fuel, it can no longer generate the energy needed to counteract gravity, leading to a collapse from the inside out, which can eventually create a singularity. In order to further investigate the nature of black holes, NASA scientists turned their focus to the core of the M87 galaxy. Here, astronomers observed an enormous whirlpool of superheated hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The sheer force of this spinning gas should have caused it to fly apart, yet it remained intact. Scientists hypothesized that a colossal mass at the center of the galaxy, weighing as much as 2 to 3 billion times the mass of the Sun, was holding it together. The only explanation for this mass was the presence of a black hole. This fundamental speed limit presents a significant barrier to the dream of interstellar travel. Even traveling at the speed of light, it would take over 4 years to reach the nearest star system, Alpha Centauri. If wormholes could somehow be stabilized, they might provide a practical shortcut, bypassing the limitations imposed by distance and time. However, stabilizing a wormhole would require an exotic form of matter, something with negative energy density, which has not yet been discovered or produced in a lab setting. Despite the theoretical nature of much of this work, advances in technology continue to bring us closer to understanding black holes. Gravitational wave detectors, such as LIGO and Virgo, have allowed scientists to detect the ripples in spacetime caused by the collision of black holes. These observations have provided yet more proof of their existence and given us new ways to study them indirectly. In 2015, the first detection of gravitational waves from a black hole merger was announced, confirming another of Einstein's predictions and opening a new era of astronomy. These waves carry vital information about the black holes that created them, their mass, their spin, and the nature of the collision. Every new detection adds to our knowledge and helps refine our understanding of these powerful phenomena. Black holes also offer a testing ground for the limits of our physical theories. While general relativity describes the large-scale structure of spacetime, quantum mechanics governs the microscopic world. These two pillars of modern physics are fundamentally incompatible in extreme environments like black holes, where both gravitational and quantum effects are significant. Solving this paradox, reconciling relativity and quantum mechanics, is one of the greatest challenges in physics. The information paradox, for example, questions whether information that falls into a black hole is truly lost forever, violating the laws of quantum mechanics. Stephen Hawking famously proposed that black holes emit radiation, now called Hawking radiation, which might allow information to eventually escape. Yet the debate remains unresolved and continues to drive research into the nature of space, time, and reality itself. In the end, black holes are more than just destructive forces. They are key players in the cosmic drama, shaping galaxies, influencing star formation, and possibly harboring clues to the very origins of our universe. As we stand on the brink of deeper exploration, aided by powerful telescopes, gravitational wave detectors, and theoretical breakthroughs, we may soon uncover answers to questions that have puzzled humanity for generations. The journey into black holes is far from over. It is only just beginning. Then light speed, which places an absolute limit on how feasible travel through wormholes is, at least with our current understanding of physics. In recent times, a particular kind of wormhole, referred to as the CR wormhole Royer, has piqued the interest of many people. This fictitious wormhole would connect two distant points in space-time, possibly even connecting various universes or different moments in time. However, critics contend that the CR wormhole may be unstable or impossible to traverse because of intense radiation and forces at the quantum level. Some physicists point out that Einstein's equations for the study of black holes and wormholes do not account for the subatomic forces governing quantum particles. To truly understand these phenomena, a new theory is needed, one that unites general relativity with quantum mechanics. A theory like this might be explained by a theory of everything, which could describe how the universe works at every scale, from the smallest particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for decades. One promising candidate is superstring theory, which holds that fundamental particles are, in fact, extremely small, vibrating strings. In this framework, the universe is viewed as a concerto, with various particles corresponding to variations in these strings' vibrations. Superstring theory also provides potential explanations for black holes, wormholes, and other bizarre phenomena by demonstrating how strings warp the fabric of space-time. Despite its potential, superstring theory remains highly speculative, as it requires extra dimensions of space and time that we cannot yet directly observe. These extra dimensions could be so tiny that they are effectively unseen by us. Some theorists suggest that these dimensions were more prominent at the beginning of the universe and collapsed as the universe expanded and cooled. Superstring theory's potential to explain wormholes, black holes, and the very fabric of the universe remains one of the most exciting frontiers of modern physics. As we proceed to decipher the mysteries of spacetime, black holes, and the cosmos itself, there is no doubt that much more remains to be learned, and perhaps even more to be discovered, about the very nature of reality. Standing at the precipice of such groundbreaking discoveries, one key realization remains. We are just scratching the surface in terms of understanding black holes and their true nature. The work of Michio Kaku in the field of string theory, and the ideas surrounding quantum gravity and its environs, have only begun to offer possible answers. Even though we've managed to gain a clearer picture, through images of black holes, advancements in technology like the Event Horizon Telescope and new methods of indirect observation, much remains beyond our comprehension. Theoretical frontier physics, specifically in the context of black holes and spacetime, is still an incredibly active area of research, where much speculation and exploration await. In addition to their obvious role in influencing the fabric of spacetime, black holes have become central to discussions about the origin of the universe itself. As string theory suggests, the collisions of universes could lead to the formation of new ones, and black holes could be integral to this process. Such a theory could suggest that our universe might have been born from a collision of two previously existing universes. Or perhaps it could even imply that we reside within a black hole itself, a concept that would certainly flip our understanding of the cosmos on its head. If this notion holds true, it could challenge everything we think we know about the Big Bang. We might begin to view black holes not just as destructive forces, but as potentially creative ones, gateways to other realms or parallel universes. While the notion that black holes could be portals to other universes, or even the key to understanding time travel is enticing, it remains within the realm of speculative science. The mechanics behind wormholes and the ability to navigate through them remain a profound mystery. Even if wormholes are stable enough to form, there's the question of whether the extreme radiation and forces near these structures would make them accessible. Some physicists speculate that if we could stabilize a wormhole, it might theoretically allow travel through time or between distant points in the cosmos. But that is still a distant dream, at least with our current technology and understanding. Moreover, if we look at black holes through the lens of quantum mechanics, we find ourselves confronted with additional intriguing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at the macroscopic level. The physics seems to break down entirely when we consider objects like black holes. This discrepancy between the theories of general relativity and quantum mechanics has been one of the most significant difficulties in physics. Theories such as superstring theory offer a potential framework for bringing these differences into harmony by introducing additional dimensions and offering new insights into the nature of gravity. But this theory hasn't yet been experimentally verified, and much of its predictions remain untested. Kaku and other theoretical physicists are working tirelessly to unite these two great pillars of physics, quantum mechanics and general relativity, into a unified theory that can explain a wide range of phenomena at all scales. A theory of everything like this would not only provide a deeper understanding of black holes and other exotic objects in the universe, but could also illuminate the very structure of spacetime itself. The concept of multiple dimensions, as predicted by string theory, may help explain the unseen forces that govern the universe. It suggests that what we perceive as a four-dimensional reality may actually be just a small slice of a much larger, more complex structure. Another area of intense study is the contribution black holes make to the evolution of galaxies and the larger structure of the universe. The discovery that supermassive black holes exist at the centers of most galaxies, including our own Milky Way, raises further questions regarding their impact on galaxy formation and behavior. It has been hypothesized that these black holes are involved in governing the development of galaxies, controlling the rate of star formation, and even playing a role in the destiny of the universe. In the end, the fact that black holes could have such an influential role in shaping the universe adds an additional level of complexity to their already mysterious nature. Moreover, the intense radiation emitted by black holes, so-called Hawking radiation, named after the well-known physicist Stephen Hawking, has led to fascinating discussions about what happens to the information that falls into a black hole. For years, scientists have debated whether information is lost forever when it crosses the event horizon of a black hole, also known as the information paradox. Hawking's groundbreaking work argued that black holes could produce radiation that slowly causes them to evaporate over time, potentially resolving the paradox. As we move forward into the coming decades, the study of black holes and wormholes is expected to evolve rapidly, fueled by both theoretical advancements and technological breakthroughs. New instruments, like next-generation space telescopes and gravitational wave detectors, are poised to offer unprecedented glimpses into the most extreme environments in the universe. Gravitational wave astronomy, for instance, has already transformed our ability to detect and study black hole mergers, cataclysmic events that ripple through spacetime itself. These observations not only confirm predictions made by Einstein's theory of general relativity, but also open the door to testing the limits of that theory under the most extreme conditions imaginable. Moreover, with the development of quantum computing and artificial intelligence, researchers now have powerful new tools to simulate and analyze the complex mathematics behind wormholes, string theory, and quantum gravity. These simulations may help us bridge the gap between existing theories and observable phenomena, pushing us closer to the long-sought theory of everything. Beyond the scientific implications, the philosophical consequences of such discoveries are profound. If wormholes or black holes are truly gateways to other universes or timelines, it challenges our notions of causality, existence, and the uniqueness of our universe. What would it mean if our reality is just one of many in an infinite multiverse? Could intelligent life exist elsewhere, not only across space but across entirely different dimensions? These questions sit at the boundary of science and philosophy, inviting us to reconsider our place in the cosmos. The more we learn, the more we realize how little we truly understand. In this grand cosmic puzzle, black holes remain among the most enigmatic and awe-inspiring pieces. They are no longer seen solely as cosmic sinkholes, but as windows into the deepest truths of reality, perhaps even the bridge between known science and the extraordinary mysteries that lie beyond. The journey is far from over. Humanity stands on the edge of cosmic revelation, where imagination, mathematics, and observation intersect. With every equation written, every particle studied, and every photon captured from the edge of a black hole's event horizon, we step closer to understanding the universe, not just as it is, but as it might be. And in that quest, the most powerful force we have may not be gravity or quantum fields, but curiosity itself.